This session will look at how standard relay tests can be extended to perform advanced assessment of more complex parameters on relay devices, such as contact over travel. It will concentrate on looking at a test that Applied Relay Testing have produced called the magnetic circuit test, which can be used to gain an insight into the contact over travel of a relay without needing to open the relay app or inspect it. This test can be done completely electronically. On the screen there are a set of standard relay tests. Fixture test to check that the relay is correctly located in the socket, test for coil resistance, contact resistance, pull-in and drop-out voltage, and timing. If I go ahead and run that test sequence, you'll see some summary result values appearing for the device. And if I open up the timing test, you can see quite a number of individual test results for timing of the relay. Basically, there are two main values for each contact, each on operate and release, for time to change state and then bounce time, and each of these values has been compared with the condition limits that you've programmed for the timing test to determine whether the test passes or fails. For quite some while, and on most Applied Relay test systems, you've been able to go into an engineering mode for the timing test, which is shown here. This is very similar to an oscilloscope display for the timing test, and it uses the capture hardware to show the exact contact activity as a graphical relationship, and using our software you can position a couple of cursors on two different events, measure the time between them, inspect various event activities, and this is quite a useful engineering debugging feature, as well as looking at adjustment of contact sets, for example. Taking this a stage further, we've created a test that we call our magnetic circuit test, and this last test here is an instance of a magnetic circuit test configured so that it makes a test on the amount by which the armature continues to travel after the final set of contact activity and before the armature stops moving, i.e. it gives an insight into the amount of contact over travel. If I go ahead and run this test, you'll see a graphical chart appear that is very similar to the timing test that you just saw. At the top here you can see contact activity against the time base across here, and underneath there are a set of analog traces. This red trace is the applied coil voltage, so the device was stimulated by a rising coil voltage that started at 0 and went up to about 5 volts. And the green trace shows captured coil current, and you'll see that the two cursors have come to rest in such a way that the left cursor is positioned on the normally open contacts beginning their closing action, and the right hand cursor has come to rest at the trough of the captured coil current. Now this trough represents the point at which the armature stopped moving as it arrived up against its movement stop. The back EMF that was being generated by the moving armature reached a peak at this point, thus reducing the coil current down to its lowest value. And therefore, by assessing the time difference or the voltage difference on the ramp between these two cursors, we've got an insight into the amount of physical movement that the contact made from here to here. Now, this activity is completely programmable. There's a script engine that has positioned these cursors under control of a set of script instructions which we can watch executing so that you can see how they can be configured. If I start the script from the beginning, you can see here the full capture trace. Here's the ramp that started at 0 and went to 5 volts. That's the drive ramp for the coil. The contact activity is shown on these upper traces here, and then the captured coil current is shown by this green trace, which reaches its trough here where the armature shuts. Now, if I step through the script, you can see the various traces being selected. This first cursor has located the specific point of contact activity that we're interested in. This is the last set of contacts to change state. The trace then opens up to be centered around that point so that we can make more detailed analysis. And with the captured coil current selected, the second cursor finds this trough, and the result is a value which is the difference between these two cursors in terms of the coil voltage ramp, 137.2 millivolts. If we close this, we can see that this is the result from the test, and using the magnetic circuit test it's possible to program a minimum and a maximum limit for that value. So in its normal operation, with the graphical display suppressed, this test executes in only around 100 milliseconds, and if we execute the test as part of an ordinary relay test, you'll see that a value simply appears, in this case 145 millivolts. That's compared with a pair of limits, and the test passes or fails. So this gives an extremely good insight into what is actually a mechanical distance. Depending on the relay type, there may have to be some correlation performed to assess the relationship between the actual mechanical movement distance and the values returned here. But as you can see, this is an extremely good insight into what in other terms might be a very, very difficult test to measure without being able to get inside of the relay. So in conclusion, Applied Relay Testing's magnetic circuit test provides a lot of customization and a graphical output that has a powerful script behind it that allows you to automate measurements on analog and contact activity parameters to extract information and values about any actual feature that you can see on the graph.